Well, good afternoon. I'm originally from Kentucky, but my adopted hometown of Huntsville, Alabama, has been known as Rocket City since before I moved here. Huntsville is a community that's used to thinking big. It sent people to the moon, it developed the engines for the space shuttle, it built the space station, it defends our country with Army missiles, and there are people here who are studying the genome to study the origins of life. These are big projects. Today, I'd like to talk to you about something that I consider to be the grandest vision that we might ever take, the biggest thing we might ever do, and that's take a trip to the stars. To understand why I think about this, you have to know a little bit about me. I do write science fiction, but I've been asked, am I soon going to become a professional writer? Well, that's only if I want to starve. My books give me a little bit of money, but I really do depend on my day job, which I happen to think is one of the coolest jobs anyone could have. I work for NASA at the Marshall Space Flight Center. And in most of the 27 years that I've been in Huntsville, I've worked at NASA and I've worked on various flight projects, research projects that you see here. And these are just some of the hardware projects. A lot of it, as you might expect, is in research. Well, I also love to talk about what I do. And my family hears this probably way too often. So one of the conversations I had with my sister Jennifer up in Knoxville, shortly after we had the conversation, she went back through the family photo albums from when I was 6 years old, sent me a picture with a note on the back in an envelope and nothing else. This is what it said. If you recognize those toys, you know what one of the coolest toys in the universe was during the 1960s when I was 6 years old, and that's Major Matt Mason. Major Matt Mason enabled me to go to the moon as a 6-year-old and to dream of going to space, and at that age, largely due to this, I knew I wanted to work for NASA. And as I read books about going to the stars and read science fiction books that took us to the stars, I knew that to do that, you should be a scientist. I had no idea what a scientist did, but I knew that the ultimate scientist, right, no offense to any other professions, was a physicist. So that's what I had to do. So I decided at about 10 years old, I'm going to be a physicist sight unseen. Well, I did that. I am a physicist. I'm also a part-time manager, and I have a wonderful job thinking about going to space. This was one of my inspirations. Now, I'm going to tell a little bit of a story that a lot of people don't realize about how much space travel and space exploration has changed our knowledge of our neighborhood, of the universe around us. Prior to 1992, we only knew of the planets in our solar system, that they are the only ones out there that existed for sure. We in science fiction, and I think the general public, believed that there had to be planets around other stars, but we had no evidence. No proof. The only planets we knew existed were the 8, actually at the time 9, planets in our solar system. One of those, Pluto, is still there, but it's no longer considered a major planet. Well, all that changed in 1992 by this. This is an artist's concept of a very distant, very energetic object in the universe known as a pulsar. Now, pulsars usually behave very regularly in the kind of radiation that they give off that our telescopes and detectors can measure and sense, but this pulsar behaved a little differently. It wasn't as regular as it should have been. And as scientists looked at the data, I didn't have anything to do with it, they determined that the only thing that could cause it to behave as it was behaving is if a really massive object, think bigger than Jupiter, were orbiting it. It was the first evidence that we had that there was a planet orbiting something else out there in space. 1992. Since then, the number of extrasolar planets that we've found has skyrocketed. This number is probably already out of date. There's probably someone or several someones who've found other planets orbiting other stars through various techniques that I'll discuss in a moment. And if you count the numbers that have been returned from NASA's Kepler Space Telescope, this number is already in the thousands of planets known to be circling other stars. That's exciting. In fact, the total number is probably in excess of 2,000 to 3,000 known. And if you look at the picture and you look at this artist's concept of our galaxy, what it might look like if you were to look down from above, and in our little neighborhood in this outer spiral arm, that little teeny circle there is all we've been able to sample looking for planets around other stars. And if the rest of the galaxy is like this little slice that we live in, then there are hundreds of billions of planets just in our galaxy, okay? Now, that's a long way from 1992 when we only knew that 8 planets existed. There are also planets that have been found orbiting stars like our sun, that the Earth orbits. This doesn't mean it's an Earth-like planet, but if you have a star like our star, the possibility of there being a planet like the Earth is possible. It could be out there somewhere. Now, this particular planet's too close to the star and too hot to be Earth-like, but the significance is there are other stars like our own with planetary systems like we have here. That's exciting. How do we find these exoplanets? The technical-minded among you might say, well, wait a minute, isn't that really hard to do? For instance, right now, I'm looking at these spotlights, and I can't see very many people's eyes out there in the audience for the glare of the lights that are shining on me. Imagine going out at night, turning on the bright headlights on your car, and you know that someone has released a flea to fly in front of the headlights. You aren't going to be able to see that flea. But our instruments have gotten better and better over the past few years, and we can now actually see a drop in the light coming from distant stars due to planets that pass in front of that star between us and it, and we can measure that. That's how the Kepler telescope was able to find so many extrasolar planets. There are other ways to do it as well. When a planet orbits a star, not only does the star's gravity keep the planet orbiting it and pull on that planet, but so does the planet pull on the star. And if you're checking the light from it very, very carefully with very sensitive instruments, you see what's known as the Doppler shift of the light. Think of this in the equivalent of sound as the sound a train makes as it's coming toward you and then passes by. It comes toward you with a fairly high pitch, short wavelength. It passes you, and the sound changes. Even though the sound coming from the train isn't really different, it's affected by the motion of the train either toward you or away from you. As this planet circles the star and tugs on that star, it moves the star, affecting the light waves coming out from the star that we can measure with our telescopes. And we can actually detect if it's a regular change, that there's a planet orbiting that star. The nearest known planet beyond our solar system is right next door, relatively speaking. That's around the Alpha Centauri system. The nearest star to us is actually 3 stars. Proxima Centauri is the closest. But of these 3 stars that are gravitationally bound, one of them has a planet around it. It's been detected and we know it's there. So in all of the stars of the galaxy, and just to give you a little scale, that image of the galaxy I had a moment ago from one side to the next is about 100,000 light years. It would take light 100,000 years traveling at 186,000 miles per second to cross that distance, okay? It takes about 8 minutes for light from the sun to get to the Earth. So it takes about 4 years for the light from Alpha Centauri to get to the Earth. It's pretty far away. How far away is this? Well, let's talk distance. We heard today experientially about someone who bicycled about 3,000 miles, okay? Well, the Earth-Sun distance is so big, 93 million miles, we can't experience that. That is such a huge number. That's not something we encounter every day, and it's a very, very large number. So astronomers invented a unit called an astronomical unit and shrink that 93 million miles down to 1 AU, 1 astronomical unit. And that way we can use some smaller number to describe these big distances that are in the solar system. I'm going to give an example of these distances that require you to do a thought experiment where instead of 1 AU, you imagine that the Earth is instead 1 foot from the sun. Imagine that the sun is where I'm standing. Relative to that, 1 AU is 1 foot away right here. That's the orbital distance of the Earth from the sun. If we go out in the solar system, we get to Neptune. Neptune is about 30 astronomical units out. 30 times 93 million miles gets into the trillions of miles and your eyes glaze over. So let's use my AU analogy. It's about 30 astronomical units. And where this young lady is standing here and about the 3rd row out is about 30 feet away from me. So in our solar system, that's about the approximate distance of Neptune. That's how long a space probe to get there would take about 8 to 10 years using rockets. On this scale, how far away is Alpha Centauri? It's 271,000 astronomical units. 271,000 feet, or about 51 miles in that direction, to the nearest star. That's a challenge, and I like challenges. So what? What do we do about that? That's impossible. We need warp drive. We need Star Trek. Well, unfortunately, the laws of physics, as we understand them, don't seem to allow us to go faster than light. We don't believe we are going to have the ability to have a warp drive to do that. So if we constrain ourselves to what we know about how nature works, we can still go to the stars. But we will have to think very big. Huntsville thinks big. This is going to be very big. Voyager has been in the news this week. It's in the news frequently. It's still operating. Launched in 1977. It's well over 120 astronomical units on its way to the nearest star system. And if it were pointed in the right direction, it would get there in about 74,000 years. Rockets are not going to take us to the stars. One of the most energetic reactions we know is a hydrogen bomb and its detonation. Just the energy contained in the motion of a spacecraft traveling fast enough to go to the stars in a reasonable amount of time, say less than a few hundred years, per kilogram of mass on that spacecraft, you have the same energy density as what produced this explosion. That's the kind of energy that has to be put into accelerating the spacecraft just to get it moving. Think big. Well, I'm going to give you some ideas of how we can go to the stars. One of those is a technology that I've worked on in my career called a solar sail. Very brief tutorial. These lights, the sun, any light that you have, as it reflects off of you, it's pushing on you. Light has no rest mass, but it does have momentum. Think of it as shooting BBs at you, and as the BBs reflect off of you, they push on you. Now, it's a very small push. Earth's gravity overwhelms it to our senses. The air handlers in here give more of a push on you than the light. But if you go out into space with a large, thin, reflective material, think a sailboat. Only think of this sail as a very thin, lightweight, reflective sail. And you put it out in the sun, it's going to move. And it doesn't require any fuel. And as you deploy these sails very close to the sun, where you get a lot more push for the amount of light that's hitting the sail, as you go inside the orbit of Mercury and you unfurl a large sail, you can get the speeds that will take you to the nearest star in less than 1,000 years. If you add to that the capability to build big lasers in space, orders of magnitude bigger than are being built by the Army right here in Huntsville, but what's being built here today is a stepping stone toward that capability. Think lasers that have an energy output equivalent to all of humanity, terawatts of energy, which we might do someday in the future. You could push these sails to a star in less than 100 to 150 years. But if you look at this scale, this roadmap I have here on the left, and you see this 1,000-kilometer diameter sail, you think that's going to be impossible. Well, fortunately, we're taking the first steps. On the left-hand side of the picture is something called nanosail. That's flown. And next year, we'll be flying a 38-meter on a side sail called Sunjammer. It's not going to another star. It's going to help us explore the solar system, but it is the first step toward giving us a capability to go to the stars someday as the technology advances. Don't ask me how we engineer a sail that's an appreciable size of the moon. I have no idea. I'm a physicist. I'll leave that to you engineers. There are other ways we can do this. One that was actually an idea of the 1960s, 50s and 60s by Freeman Dyson and others is Project Orion. Orion's very simple. It's a brute force way to go to the stars. Imagine an aircraft carrier with big shock absorbers, think the size of this building underneath it, and pusher plates underneath that, huge, under which you detonate repeatedly, once every few seconds, a hydrogen bomb. Okay? You may laugh. There were experiments done with this with conventional explosives. It works. Theoretically, you could use this to get to an appreciable fraction of the speed of light and travel to the stars. I'm not advocating we do this. This would be a very bad day for the planet, but it is theoretically possible. As we're doing research in understanding the universe and nuclear fission and nuclear fusion, the reactors at Bellefonte and the nuclear plants are not energetic enough to get us to the stars. We need to have the next step, which is how the sun produces energy, and that's nuclear fusion. Fusion is real. It's been done in the laboratory, but right now we put more energy in than we get out. And we have to go way beyond that to build a starship with fusion power. We have to get a lot more out than we put in. You see here by the numbers that the spacecraft that would use fusion, if it can work, would be big. it would be very big, tens if not hundreds of thousands of tons. And for Huntsvillians, this is what it compares to with the Saturn V, okay? So you look out at the horizon as you're going home and imagine the model at the Space and Rocket Center in 500 years, okay? We can go. This is not impossible. It's just really, really hard. Now, the ultimate way to go to the stars is to use the energy of nature itself, matter, antimatter. Very briefly, antimatter is not the stuff of science fiction. Antimatter is real. There are protons, there are antiprotons. There are electrons, there are positrons. They're very rare. They come into contact. It's the most efficient form of matter to energy conversion we have. It's E equals mc squared. It is the ultimate drive for an interstellar craft. This is an artist's concept of what might look like. Imagine this the size of Florida. How much antimatter does this take? Well, today we produce about 1/1000th of a gram of antimatter per year, a nanogram. We need thousands of tons of antimatter to do this. It would be a bad day if that went off accidentally. We're going to do this on the outer planets. We're going to do this in space. It'll take a civilization that spans the solar system to do this, but the laws of physics say it can be done. The galaxy is full of planets. Some may be just like the Earth, most are not, but they're there. It's our neighborhood. Nature has not written the laws to keep us out. What we have to do to get there is we have to use the talents and the minds that we have. We have to have long-range vision. We have to be visionary, and we have to think really big. Thank you very much.